Engineering system always change with time, and mathematics explain that change through ordinary differential equation ODEs. Our first problem is phone battery charging, showing how energy build up in electronics. The second is water tank draining, showing how fluid flow and pressure drop. Both are everyday process, yet both follow the same exponential law, proving how mathematics connect directly to real engineering.
For the calculation part, first thing first, we need to assume that charging rate is proportional to the difference between maximum charge minus current charge. And we will get dq over dt is equal to k constant times difference between maximum charge and current charge, which is our ODE. Now we're going to solve this ODE by using integration is a separable equation, and we will get the general equation with variable k and c, which is q at given time is equal to q max minus e to the power of negative kt times c. From our experiment, data shows that q at initial is 20% and also q at 30 seconds is 64%. Thus, we're going to just substitute this value and we will get the general equation, which is q at given time is equal to 100 minus e to the power of negative 0.02660 times 80.
During the initial phase of charging, the charger delivers a nearly constant current to the battery, which means the battery percentage increases at a relatively steady rate. Hence, dq over dt is roughly constant. However, this phase is not directly modeled by dq over dt because the term q max minus q would be large and relatively constant, implying a constant rate. When the battery approaches its full charge, for example above 80%, the charging strategy often switches to a constant voltage mode, where the charger tries to maintain a constant voltage to avoid overcharging and damaging the battery, which the current delivered by the charger decreases as the battery gets closer to 100%. And also, a decreasing charging current means a decreasing rate of charge of accumulation. Overall, the entire charging process isn't perfectly described by this single equation due to complex charging protocols. So the equation given is an excellent model for the recovery and performance optimization of smartphone battery charging, where the rate of charge accumulation slows down as the battery approaches its maximum capacity. It also captures the behavior of the system approaching its limit, which is 100%.
Let us proceed to the calculation by modeling an ODE equation with respect to Torson's law. Torson's law states that velocity of an acid fluid is equal to 2 times gravity times height. As we all know, volumetric flow rate equation is Q is equal to area times velocity. From these two equations, we will get Q is equal to A times Z to GH. Next, we need to relate this equation with volume of a cylinder tank equation, which is P is equal to area times height. So we take derivative of both sides and we will get dV over dt is equal to dAh over dt. Using the principle of conservation of volume, dV over dt is equal to input minus output, which is 0 minus area times Z to GH. And we will get dH over dt is equal to negative K times ZH, which is our ODE. Now, we need to solve this ODE by using integration by using separable equation. Then, we'll finally get the general equation with variable k and c, which is h at given time is equal to negative k times time over 2 plus constant to the power of 2. From our experiment, our data shows that height at t equals to 0, which is an initial, is 12.7 and height at 20 seconds is equal to 10.2. So we need to just simply substitute this value in the general equation to get the k and c value. So, in the end, we will get the final general solution, which is h at given time is equal to negative 0.0185 times time plus 12.7 to the power of 2.
The equation dH over dt negative k sub h is an excellent model for calculating water draining in a tank, where the flow rate of water flowing out slows down as the height of water reaches the outlet hole. During early draining, tank is still full of water and the height of water in tank is really tall, creating higher pressure to force water out. As the tank continues to drain, water height becomes smaller, reducing pressure. As a result, flow rate of water is decreased and water level drop more slowly. This behavior can be observed in graph where curves become less steep over time. The ODE model accurately captures this changing drainage rate and allow engineers to predict the water level at any given time. These results are important for designing emergency water storage system because they help engineers estimate how long a tank can provide water before it becomes completely empty.